We can start now.
Thank you, Mateus. Welcome everyone to today's seminar. Today it's a pleasure to introduce Josiah Schwab from the University of California, Santa Cruz in the United States. Josiah earned his PhD at the University of California, Berkeley. He has broad interests in stellar astrophysics, stellar physics and stellar evolution, and is one of the developers of the open source code Modulus for experiments in stellar astrophysics. Much of his recent work has focused on white dwarfs in binary systems that accrete from companions or merge with other white dwarfs, with the goal of understanding the origins of transient events like supernova and the formation channels of unusual types of stellar remnants. Thank you so much, Josiah, for accepting our invitation. You may start when you're ready.
Thank you. So white dwarfs are the most common kind of stellar remnant. So they're what's left behind after the evolution of low mass stars. So stars about 8 times the mass of the sun or below. And for most white dwarfs, after they form, they just kind of quiescently cool. And that's kind of illustrated here in the left image, which shows the nearest white dwarf to the sun, Sirius B, which is indicated by this arrow here. You know, it's a faint thing compared to its much more luminous main sequence companion. These things are 100th or 1000th or even less of the luminosity of the sun, but they're quite common. And in the kind of 20 parsecs around the sun, there's sort of more than 100. And there's another fun flip side of white dwarfs, which is that for some small fraction of them that manage to interact with the binary companion, they can explode as supernovae and go from being these incredibly faint things to, for a brief time, for a week or two, kind of outshining their host galaxies. And that's shown here with a kind of type 1a supernova indicated by the arrow. And while these are incredibly rare, that you maybe only have one per galaxy per 1,000 years, because they're so luminous, we can, for example, see them across the universe. And they have become an important tool in distance measurements and in cosmology. So I think one of the fun things about working on white dwarfs is kind of the many different faces and manifestations that they have in astrophysics. Now, if you like one white dwarf, what's better? 2 white dwarfs. And so today I'm going to talk a lot about white dwarf binaries. And the way you make a white dwarf binary is by starting off with a binary of 2 main sequence stars, having them live their lives, possibly interacting. And then at the end of the day, each one of them leaves behind a white dwarf. And because there can be a huge range of initial periods of normal main sequence star binaries, there's also a very wide range of double white dwarf binary periods. But the ones I'll really focus in on today are ones that are close. So they're born with periods of something like a few hours or less. And the reason that's interesting is because these binaries emit gravitational wave radiation and lose energy and angular momentum and inspiral. And if you're born at a few hours or less, in less than the age of the universe, these white dwarfs can come close together and merge. And a white dwarf is an object that's about the mass of the sun, supported by electron degeneracy pressure, and ends up having about the radius of the Earth. And as a result, the orbital period can really shrink quite dramatically down to as small as a few minutes before the kind of larger white dwarf doesn't fit inside its Roche lobe anymore, and material is forced to become transferred from one to the other. And one of the interesting things about white dwarfs being supported by electron degeneracy pressure is that there's kind of an inverse mass radius relationship, so that in a binary, the larger star is the less massive of the 2 white dwarfs. And so when these things begin to get close, material is going to be transferred from this larger, less massive white dwarf to the more massive one. And so when a white dwarf binary, when mass transfer starts, well, what happens? Well, one of the things that's interesting is even before then, because these objects are emitting gravitational waves, they're emitting gravitational waves with kind of millihertz frequencies because they have orbital periods of order minutes. And this is something that in the last kind of decade, photometric surveys looking for white dwarf binaries have dramatically increased the number of systems we know that are close enough to the Earth and have sufficiently small periods that their gravitational wave radiation is likely to be detectable when in the next decade, in the 2030s, people develop missions like the LISA mission, which is a space-based gravitational wave interferometer. And so we already know of binaries, of double white dwarf binaries. Many of them are shown in this plot as a function of their gravitational wave frequency and basically how strong the gravitational wave signal is. And all the things about this black line are binaries that when this LISA mission flies, will be verification sources where we know that there's going to be a gravitational wave source at the location of this double white dwarf binary. Now, double white dwarf gravitational wave sources are somewhat different from the gravitational wave sources we've heard a lot about recently from LIGO, where in the LIGO case, in the double neutron star or double black hole case, you're actually seeing the merger event itself. In the case of these double white dwarf binaries, when you detect, say, a system like this, it may still be 100,000 years before merger. So in our human lifetimes, we're not going to get a chance to actually watch it merge. But nonetheless, we'll detect it and we'll characterize it, and we'll know that there's a lot of systems out there that on astronomical timescales will merge. And so then the interesting question becomes thinking about when these close white dwarf binaries do merge, when they get close enough for mass transfer to start, what happens? And there's a really quite wide range of possible fates for these objects. So if I start here with kind of some hypothetical white dwarf binary, one thing that can happen is that as mass transfer proceeds, that the mass transfer could actually be stable. And so what could happen is that just mass is transferred from one star to the other, and that process just continues happily for millions or maybe even billions of years. For the aficionados in the crowd, we think the AMCVN stars may be instances of something like this happening. Another possibility is that the start of this mass transfer could lead to a supernova explosion, like the one I showed in one of my early slides. And that's, of course, a very interesting question and one that we want to understand more about what exactly could cause this explosion, exactly which systems explode. But I won't talk much about that today. If there's no explosion, then I have these two objects. And one of the interesting properties of white dwarfs is also that they have a maximum mass, which is called the Chandrasekhar mass, and is about 1.4 times the mass of the sun. And so if the kind of total of sum of the masses of the two white dwarfs that merged was in excess of that, then it seems likely that the object kind of is destined to collapse to a neutron star. But if the sum of the two masses is less than that, then at the end of the day, it seems that the object that's left behind is likely to eventually return to being a single white dwarf. And that's really what I'm going to focus on today. This pathway of taking two individual white dwarfs, merging them, maybe having some stellar evolution happen in between, and then at the end of the day, ending up with a single white dwarf left behind. So to understand kind of what that means and what happens at the end of that process, I want to kind of talk through what really goes on sort of during and after a double white dwarf merger. So the sort of picture to have in your head and is something that's really informed by hydrodynamics simulations of the merger process. And there's a few snapshots from one calculation by Dan et al. Shown in this figure here. And again, there's a simulation starting here with two white dwarfs, a larger, less massive white dwarf, and a smaller in radius, more massive white dwarf. Here, the lower mass white dwarf, you can already see it's been tidally distorted by the gravity of the more massive companion. And as it inspirals, material begins to be transferred from the secondary to the primary. Here, that process is unstable. So once a little mass transfer starts, the mass transfer becomes more and more rapid. until this less massive white dwarf ends up being tidally disrupted and essentially ends up being spread out in a disk of material that surrounds a mostly undisturbed primary white dwarf. And so we've gone from having two objects to this one object with kind of a core and a disk. And so what next? One of the reasons that it's actually been fruitful to think about this kind of evolution is you can really divide what next into a series of relatively well-separated phases with well-separated timescales. And so I described to you sort of the dynamical timescale where this mass transfer becomes unstable. And that runaway process is happening kind of on the orbital period of the system. So that means that in something like minutes, this kind of tidal disruption procedure has completed. And so now you have this disk of material, and that disk can be unstable to various magneto-hydrodynamic instabilities that lead angular momentum to be transported through the remnant. And the time scale for that to happen is likely to be on kind of hundreds or thousands of orbital periods. And so at that time, you have torques, kind of, again, moving angular momentum through the remnant. But the really important thing is that this remnant is very optically thick. It's very dense. And so it can't radiate away the energy that was deposited in the merger. So the post-merger material is quite hot. You've liberated a lot of gravitational potential energy and converted it to thermal energy during this merger process. But it will take thousands of years before the remnant is able to adjust and actually be able to shed this energy, because it's not dense enough to be cooled by neutrinos, which would be very rapid cooling. And the photons just can't leak out. And so when we study this kind of problem then, one of the kind of ways I've approached this is to take simulations of kind of that early phase of the merger, continue those simulations, understanding how that disk of material evolves and how essentially these viscous stresses and transport of angular momentum take you from a configuration where you have a kind of rotationally supported disk and you have something that's kind of extended to where that rotation gets converted to thermal support through viscous dissipation, and you end up with a relatively spherical hot remnant. And now the question from there is what happens next? And to follow that question, you start, again, thinking what happens on the thermal and nuclear timescales of this object? How is energy going to be transported through this remnant? How will nuclear reactions generate energy? And at that point, it really turns into a stellar evolution problem. And so that's something I'm very interested in, and I work a lot on developing stellar evolution software. And so the kind of basic then thrust of this research is doing things like taking initial conditions from double white dwarf mergers, using those to initialize stellar evolution calculations, and then asking what happens as we go from the merger to essentially whatever's the final fate of this object. And I think one of the really fun things about that sort of evolution is that the merger gives an opportunity to take two essentially, stellar cinders. The white dwarves are done. If they were in isolation, they would quiescently cool, but they're combined and they have a chance to essentially become a star again and have another second life of kind of nuclear reactions. And as a result, you kind of form unusual kinds of stars through white dwarf mergers. In particular, because the white dwarfs have already shed their hydrogen envelopes, the stars you make are generally hydrogen deficient. And so let me kind of walk you through some of the classes of stars that we think form through these sort of mergers. So if you take two helium white dwarfs, which are relatively low mass, and you merge those together, they have a chance to restart core helium burning. And that phase of evolution is a lot like the phase of stellar evolution you would have in a normal hydrogen burning star if you were, say, sitting on the red clump, which is a phase where you have core helium burning, but in a big hydrogen envelope. So there's a set of stars that are kind of hot subdwarf stars, SDO and SDB stars, which are core helium burning, but with very small hydrogen envelopes. And we think those are formed through these mergers. And at the end of their lives, once they've gone through this second revitalized phase, again, they're going to leave behind a white dwarf, in this case, probably a carbon-oxygen white dwarf of something like 0.6 solar masses or so. If you change the compositions of the white dwarfs that you're merging, you can get a different result. And so, for example, if you merge a helium white dwarf on top of a carbon-oxygen white dwarf, you have the opportunity to set up a helium burning shell on top of a carbon-oxygen core. And that configuration is like what you might find in the interior of an asymptotic giant branch star, again, except without the hydrogen envelope and hydrogen burning shell, because these are hydrogen efficient. And there's a class of stars, the R Corona Borealis stars, which seem to fit into this picture of giant helium shell burning stars. And again, if we take models and follow those through their lives, we think they're going to, again, leave behind single white dwarfs, here a little more massive, something like a 0.8 solar mass carbon-oxygen white dwarf. The case I want to talk a little bit more about today in detail is the merger of two carbon-oxygen white dwarfs. And here you have the chance to, again, now start carbon burning and have a situation similar to the kind of most massive low mass stars, so something like 5 or 6 or 7 solar mass stars, where in the deep interior, there's off-center carbon burning. And that's the process that we think then eventually will lead to the creation of oxygen neon white dwarfs. And so that gives us a chance to leave behind relatively high mass, say 1.2 solar mass white dwarfs. And one of the interesting things is that we don't really know a kind of pre-existing class of stars that we necessarily want to invoke these carbon-oxygen white dwarf mergers to explain. So one of the questions is, well, what do these look like after the merger? And how can we find those things? And then what are the white dwarfs that they leave behind like? And so one of the reasons I want to focus on these is because the white dwarfs that these sort of mergers leave behind are likely to be ultramassive. And by that, I mean in excess of about a solar mass. And that turns out to be a really good place to look for the evidence of single white dwarfs formed from white dwarf mergers. Because if you want to make such a massive white dwarf from a single star, you need a relatively massive main sequence star, something like 5 or 8 solar masses. And those stars are relatively rare because the initial mass function of stars are such that more massive stars by number decrease quite rapidly with increasing mass. And so as a result, it actually turns out that an important channel to make massive white dwarfs is to start with 2 low mass white dwarfs, which are much more numerous because they were produced from, say, 1 or 2 solar mass main sequence stars, which are themselves much more numerous, and then to combine those and make this more massive white dwarf. And even though not, every binary works out so well to give you something that will merge, the fact that there are so many more of these lower mass stars actually means that this channel can be a significant contribution. And population synthesis studies, again, suggest that this could, be 20, 30% of massive double white dwarfs. And there's some observational evidence of this too, which I'll come back to. But the basic point here is a plot showing as a function of white dwarf mass, kind of what fraction of white dwarfs show some indication of being a merger product. And at lower masses, say 0.8 or 0.9, that's maybe 5 or 10%. But by the time you've gotten up to these more massive white dwarfs, this looks like maybe 30 or 40% of the massive white dwarfs we see show indications of going through mergers. And so that really motivates trying to understand what the properties of these massive white dwarfs look like, because there's a good chance for us to pick them out of the massive white dwarf population. So what are their properties? So I'd like to try to kind of, in one diagram, summarize a lot of my work in the last, say, 5 years. And so this is a really schematic, simple kind of HR diagram showing basically how does a merger remnant evolve. And so phases where the merger is redder or cooler are over on the left. Phases where it's bluer and hotter are on the left and on the right. So bluer, hotter here, cooler, redder over here. And more luminous phases are near the top and less luminous phases near the bottom. And so the kind of broad brush evolution goes as follows. You start off with the merger happening and creating some initial condition. You have relatively rapid transport of angular momentum that kind of redistributes material internally. And then because of the energy deposited in the merger, the object begins to puff up and it swells to become a giant. So something with radii of hundreds of thousands of times the solar radius. And during this giant phase, it's puffy and it's trying to radiate the energy that was deposited in the merger. During that phase, because you have cool material and you have a lot of, say, carbon and oxygen around, there's also the chance that you have this kind of cool, luminous, dusty object that has a chance to expel material through stellar winds. And then after a while, after something like maybe 10,000 years, when it's radiated a lot of its energy away, it begins to shrink and become bluer and a smaller radius. While it was so large, the fact that it had all the angular momentum around from the orbital motion of the merger was not such a big problem because it had a huge moment of inertia. But as it shrinks, the rotation will become more and more rapid until you can reach a point where the object starts rotating at critical rotation, where essentially material has the Keplerian angular velocity such that the outer layers of the star would just say want to orbit. They can be supported by rotation alone and not by pressure. And if you follow remnants through this phase and you kind of make the assumption that the most angular momentum an object can hang on to is the amount of angular momentum that would cause it to rotate at this maximal rotation rate, then there turns out to basically be a minimum during this phase. There's a bottleneck where if you just force that to be true, during this phase, the object will shed a certain amount of angular momentum. It will come out of that phase, and then it'll never be critically rotating again for the rest of its life. But that process sort of sets a kind of maximum amount of angular momentum that you can retain. And so if you continue then to follow the object through any kind of burning that it goes through, any sort of carbon burning or neon burning, and follow it on, if it takes this track where it's less massive than the Chandrasekhar mass and becomes a white dwarf, then it just finishes its evolution and is now going to quiescently cool as a single white dwarf for millions and billions of years. But that assumption about the angular momentum that we could keep implies that when we reach this kind of single white dwarf stage, white dwarfs coming from these mergers should be relatively rapidly rotating. They should have rotational periods of something like 10 or 20 minutes, which is much more rapid than the kind of single white dwarfs that we usually find from single stellar evolution. So we find some indication already of what one property that would distinguish a single white dwarf formed through a merger from a white dwarf formed from single stellar evolution. And one of the important questions is also, what's the composition of this white dwarf? And one of the things that my work has found is that essentially, even in the merger process, the transition between where the interior composition remains carbon-oxygen and where the interior composition shifts to being oxygen-neon happens in a very similar way as in white dwarfs produced from single stellar evolution. And so what that implies is that white dwarfs of about 1.05 solar masses or less for mergers can remain carbon-oxygen white dwarfs. But if they're more massive than that, the burning that happens during this after post-merger evolution phase converts the interior to oxygen neon. And then the white dwarf that cools has that composition in its core. So that's the sort of basic story. And now the question we want to do is we want to confront that from observations. And it's been an exciting few years in terms of thinking through how this picture might fit in to what we actually see in nature. So first, I want to start by telling you about a peculiar individual object. So here's a nebula that's detected in the infrared. So there's 4 postage stamps here with kind of different wavelengths or different intensity scales, but all on the same spatial scale. And in these kind of infrared images, ABC, you see basically a parsec size nebula. And if you look at the exact same region in H alpha, so looking for hydrogen, there's basically nothing. And so that looks very different than the kind of sort of normal planetary nebulae that are hydrogen rich and surround white dwarfs that are being born. So the question is, how might you get such a hydrogen free nebula? And to understand that a little more, there's also a central source at the center of this nebula. And this paper by Dwarfs et al. In Nature a couple years ago studies both the nebula and the central source. And the central source is a hot Wolf-Rayet type star. So it's a hot blue star with a quite hot effective temperature and a significant luminosity. We have a good sense of the distance from Gaia. And there's a spectrum. And the spectrum shows lots of carbon and oxygen lines and not much helium. In fact, no helium to detected limits. And so what that implies is that here's an object with basically a hot hydrogen and helium-free object, probably in a hydrogen and helium-free nebula. And for those of you who have some experience looking at spectra, one thing really stands out here, which is the incredible width of these lines. And that's actually because their velocities, which I'll come back to in a little bit, are 16,000 kilometers per second. So that's kind of almost supernova-like velocities. So this stellar wind is very unusual and has a significant mass loss rate of probably something like 10 to the minus 6 solar masses per year. And so one of the exciting things about this nebula is that it actually really nicely fits in to that schematic story I told you a little while ago. So this plot in the background here is an HR diagram from a calculation in 2016 before the characterization of this object, showing more quantitatively one of the evolutionary tracks I kind of outlined for you earlier. And this actually nicely explains the presence of a hot blue source in a hydrogen and helium-free nebula, because you have a white dwarf system, in this case, a kind of merger of 2 carbon-oxygen white dwarfs, evolving for a while through a phase where it's large and giant and has mass loss for something like 10,000 years. And if you assume it's shedding kind of carbon and oxygen-rich material from its surface at, say, 100 kilometers a second for that 10,000 years, the kind of mass loss during this phase can explain the formation of a kind of parsec scale nebula. And then after that's formed, the central object evolves to the blue. And this kind of calculation, again, predicts the presence of a hot blue object inside such a nebula. And it predicts that it should have a luminosity that's intermediate between kind of other sorts of stars we know. So there are Wolf-Rayet stars from massive stars, but they are kind of at luminosities up here. And there's also stars from kind of normal planetary nebulae, but they have luminosities, say, down here. And so the kind of object in the center of the nebula actually fits pretty well into this picture of being a merger remnant. But there remains a puzzle, which is this very strange wind, which has a velocity that's much, much greater than the escape velocity. And if you ask how much energy is being injected into that wind, it's actually a luminosity that's greater than the luminosity of the stellar surface. And so the suggestion is that this object then this wind is potentially being powered by rotation through the intervening action of magnetism. And it actually seems quite likely that double white dwarf mergers generate significant magnetic fields. You have this phase of strong differential rotation that we think generates and amplifies magnetic fields. But one of the interesting things is the merger model that's shown in that previous plot doesn't make the prediction that the object has a rapidly rotating core at this particular time. So there's a little bit of a tension and a mystery here of how do we explain the kind of wind properties of this object and how do we associate that with the central source. But I think this is a really tantalizing example of an object that may be a white dwarf merger remnant, something like 10 or 20,000 years after merger. And I think there's a lot of opportunity for follow-up and modeling to understand a little bit more about what this means and whether and how we connect this object to the, say, white dwarfs that may have formed it. Now, one of the things about that particular object that I just mentioned is that it's not a white dwarf yet. And maybe it'll never be a white dwarf. We don't know actually how massive that central remnant is. And so the next thing I want to talk about is really specifically talking about observations of white dwarfs themselves and where we may see evidence of the existence of mergers in this. And so I'm going to take very much a white dwarf population standpoint here. And one of the things that's really been happening in the last few years is that the Gaia mission, which has measured the brightnesses and proper motions and distances to 1 billion stars, has really done a tremendous amount for white dwarf science. The figure on the right is a color magnitude diagram showing basically the white dwarfs from the Gaia data release 2. And already you can see that there's all sorts of structure in here. There's bands like here, there's this spur here. And these in this diagram are labeled by A, B, and Q, corresponding to the spectral types of the white dwarfs that are common in those regions. And those correspond to basically different surface compositions, different atmospheric compositions of the white dwarfs. So A's are hydrogen rich, B's are helium rich, Q's have carbon. And to really get more information on that, you want not just Gaia, but you want spectroscopy to follow up the white dwarfs to really better understand the surface compositions. And that's one of the things that's really been happening, and it happened already, also some with SDSS. But we're now having the opportunity to basically take, say, the 10 to the 4 white dwarfs that are within 100 parsecs of the sun and really completely characterize them in a way that's never been done before. And so what does the structure that we saw in that diagram mean? So here's basically the same color magnitude diagram. The black points in the background are quite similar. But now there's some theoretical tracks to help us interpret things. And the statement is most of those bands that sort of moved from the upper left to the lower right correspond to the cooling of a white dwarf of essentially a single mass. So these sort of stripes are basically watching, okay, here's a sequence of a lot of white dwarfs that are all about 0.6 solar masses and are just in different stages of their cooling. And as you move towards the left of this diagram, because the white dwarfs are getting smaller, they're actually more massive. That's that inverse mass radius relationship. And so more massive white dwarfs are sitting over on this left-hand side of the diagram. And that one feature, which was labeled Q in the previous diagram, is sitting kind of here. And that is very much not a track of constant mass. And so when you see a feature like this, basically what this tells you is I'm moving along a cooling track, but during that phase, there's some sort of delay. There's some sort of additional energy source such that I'm having to spend extra time sitting in this region radiating that energy. And what we think this branch is here is crystallization. So that there's extra energy being released as the dense plasma inside the white dwarf undergoes a phase transition from liquid to solid. And that extra delay may be related to the latent heat of that transition. And so that can kind of explain the location of this feature occurring around when that crystallization happens. But there's still a kind of a puzzle there, and when that sort of feature ends up being named the DQ branch, the Q branch, because there's actually a lot of DQ white dwarfs on it. And when people study white dwarfs of that spectral type, and this is largely drawing on a paper from Couteau, there's a histogram here of the masses, and there's a secondary basically bump. So there's a set of low mass DQ white dwarfs, but then there's also a set of kind of high mass DQ white dwarfs around 1 solar masses. And if you look at what do the compositions of those white dwarfs look like, so this is a plot of effective temperature versus basically carbon to helium ratio, those massive white dwarfs really stand out. And there's a relatively well understood sequence for the lower mass white dwarfs, but for these higher mass white dwarfs, they're much more carbon rich and don't fit into the understanding of the lower mass white dwarfs. And so there's basically some interesting, unusual population of massive white dwarfs. And so one of the kind of really natural suppositions has been that this may be something associated with mergers. That also helps explain potentially why these objects are carbon rich. And in studying the kind of Q branch, one of the sort of exciting results in the last couple of years has been unlocked again by Gaia, because Gaia also tells you about the velocities of the white dwarfs, at least in the plane of the sky, so the transverse velocity. And because these objects are in the galactic disk, there's a relationship between their age and their velocity dispersion because of the kind of interactions between these stellar systems and other stars in the galactic disk. And as a result, essentially how fast something is moving tells you something about the age of the system since its formation. And it's that kind of a probe that was used to kind of infer that, for instance, a significant number of massive white dwarfs may be merger products, because the overall age of a white dwarf formed through a merger is older than a white dwarf formed from a single star evolution, because you had to wait longer for the initially lower mass stars to evolve, and because you also had to wait for the merger to occur. And when you look on the kind of Q branch, there's also a set of objects that have kind of very high transverse velocities, which are indicated here, again, in this AHR diagram by color, and they're colored this strong kind of magenta. And there's actually indication that this delay is extremely long, not just the delay from merging, but that there's some additional delay that's maybe 8 gigayears or so, where objects are cooling, but then they just sit on this branch for a very long time. And many of the objects sitting on this are these unusual DQ white dwarfs. Now, then one of the interesting things is, if you say that the region where that delay is occurring is associated with crystallization, then where crystallization occurs depends on the core composition of the white dwarf. And we see, again, this is basically the same plot as before, but colored differently, now with solid lines showing where CO crystallization happens and dashed lines showing where oxygen neon crystallization happens. And it seems like these white dwarfs fit in much better with being CO crystallization rather than oxygen neon crystallization. And that's actually quite interesting, and from my standpoint, quite puzzling, because one of the predictions from my own work on white dwarf mergers is that the kind of objects that we form at high masses from white dwarf mergers, at 1.2 solar masses, say, ought to have oxygen neon cores. But this sort of delay is in tension with that. And so I think there's a real mystery here, again, of what exactly are the properties of objects formed through mergers. And also just really, are these cooling delays that are being seen related to mergers? So they're not just the fact that you have to wait for mergers. You really need some other additional delay. And one of the proposed ideas was that this reflects an additional energy source related to gravitational settling that happens near crystallization. And that's something that we've kind of suggested, but we don't know for sure whether it works. And there's some indications that maybe settling can't be as rapid as needed. So this is something that we need to keep exploring. And along similar lines, there's a suggestion that this kind of delay may reflect a different chemical composition of merger products that maybe lets you get more energy out kind of during this sedimentation and crystallization phase. And so to sort this all out, what we really need are kind of more photometric and spectroscopic observations that can really focus and characterize these ultramassive white dwarfs and to look for other kind of merger signatures there. And I think some of the most promising ones to look at are likely the rotation rate of these objects and also potentially the occurrence of magnetism and strong magnetic fields. So just to kind of summarize, I'm really excited about the coming decade because I think we're really set up for a really fun interplay of observation and of theory because there's all these new observations from Gaia that are really, and from the photometric surveys like ZTF and the ELM survey, basically that have expanded our knowledge of close double white dwarf binaries. And we now know many tens or even 100 close double white dwarf binaries that are destined to merge. And knowing that happens, then we want to start looking for what the remnants of those mergers are. And there's this kind of already one really interesting potential merger remnant, this unusual hydrogen and helium-free infrared nebula that might be a merger remnant shortly after merger. And then by following up the Gaia sample of white dwarfs, especially those where we can get really nice data within about 100 parsecs, I think we're going to be able to start to get a kind of that complete characterization. And that sample is going to include a significant number of massive white dwarfs that are merger products. And so we can start testing our theories and trying to understand really what are the signatures of single white dwarfs that were formed through mergers. And, in that really fruitful decade, then by the time we enter the 2030s and start to get these millihertz gravitational wave observatories that are measuring double white dwarfs through gravitational waves, and we've also followed those up through electromagnetic observations, we're going to put together this picture of what the compact binary population is in the Milky Way. And then we're also going to have the theoretical understanding necessary to interpret, basically, given that white dwarf population, what are the outcomes of those mergers and how do they fit into the other sorts of things that we see in the Milky Way today. Thank you.
Thank you very much for your talk, Josiah. For the people following us on YouTube, please post your questions if you have any on the YouTube channel, and our speaker will try to answer them later. And next week, we'll be back with a seminar on hosts of early ionized bubbles at Redshift 7 with HST, Muse, and ALMA by Davi Sobral. Thank you. Now to the